Hello, how are we doing? This is Mike here, and in this video we're going to keep our discussion of differential equations moving. We want to keep moving with this topic of differential equations, but specifically we're going to talk about solutions. Solutions of a differential equation versus a general solution of a differential equation. So differential equations have particularly different forms of solutions. You're going to see that there is going to be usually a general solution, one that describes more than one circumstance of a solution for a differential equation. And then you might have a particular solution where every value is defined and you can go ahead and solve that differential equation, usually by taking multiple derivatives. So let's go ahead here and define a differential equation as dy dx is equal to f of x comma y. So this is going to be a differential equation of f of x comma y. Oops, where did this go? dy over dx is a function of xy. So this is a function of both the x variable and the y variable, the independent variable and the dependent variable. So they both can be changing simultaneously to solve. They can both be changing simultaneously to solve. So let's just look at a basic example of what this really means. Sometimes people get a little hung up over this notation here, but I try to tell people not to worry too much about it. So an example of an above differential equation could be dy dx equals to 3x plus 2y. Notice here we have a variable x and a variable y. So we see that x and y can have values in our differential equation. That is this equivalent right here. So this is our f of x comma y. That's a horrible y. X comma y. So when we look at this, we recognize that, how do I go ahead and find this? We can go ahead and define a solution to that differential equation by being able to take the derivative of some equation y sub x, and this has to equal to that function of x and y sub x. Taking the derivative of some solution. So this solution, we're going to let that solution be y of x. And if we take the derivative, it would have to satisfy this right here. So let's go ahead and look at an example. And sometimes examples are easier for me to see these definitions. So let's go ahead and look at the differential equation dy over dx minus y is equal to e to the 2x power. So e to the 2x power. So if we look at this, we can say that this is a first order differential equation. This is a first order differential equation. It's first order because this is a value of the derivative and it's a first derivative. So it is a first order differential equation. Excuse me. So if we want to, oh, where did that go? Why is it just deleting things on me? That's horrible. I sneezed and it's gone. So I said it was dy dx minus y equals to e to the 2x power. So let's say that I go ahead and give you a solution. And this solution to this is y equals e to the 2x. I'm going to make a special note over here discussing solutions. So give yourself a little bit of space so we can look at a relationship between solutions and these arbitrary constants we're going to discuss in a couple minutes. So if we want to check to make sure that this is in fact a solution of the above differential equation, let's go ahead and find y prime. So hopefully we all recognize that we are going to apply the chain rule and we get y prime being equal to 2e to the 2x power. Everywhere we see the first derivative, we're going to plug this in. Everywhere we see y, we're going to plug this in. So instead of us having dy dx minus y, we know dy dx is equal to 2e to the 2x, and we subtract off our original function, which is e to the 2x. 2e to the 2x minus e to the 2x is in fact equal to 1e to the 2x, and that's what we have here. 1 equal to the 1e to the 2x. So we see that this is a solution. This is a solution. A solution. I will tell you that y equals e to the 2x is not the only solution to the above differential equation. It's not the only solution. So there is a general solution. There's a general solution that contains all possible solutions to the above equation. So a general solution contains all possible solutions to the differential equation. So a general solution contains all possible solutions to the differential equation. General equations, they have constants that are arbitrary. So the general equation of the solution to the above differential equation, which was dy dx minus y equals e to the 2x, the general solution is going to be e to the 2x plus c e to the x. So at this point, don't feel worried that you don't know how to get that solution. I think it's just more important for us to define the different types of solutions. So this is a general solution. And it has a constant of integration. This has a constant, not a constant of integration, so don't do that. It's just a variable constant. So as I told you to write this note above here, this note, here's where you can fill in this note. So this is something that's important, and it just sort of helps to identify some trends in solving differential equations. I always like to identify trends to help me check my work. So a first order differential equation. A first order differential equation has a single constant, that is arbitrary. So that is arbitrary in its general solution. So notice a first order has a single arbitrary constant. So usually, and this is, I'm putting a usually, and this is 99.9% of the times, the general solution, oh, where did that go? Okay, so I don't know where my prior writing went. I don't know why, it's just deleting things on me. The general solution of an nth order differential equation has n arbitrary constants. So before I said that we had a general solution of y equals to e to the 2x plus c e to the 2x. Yeah, that's what it was. E to the 2x plus c to the 2x. Notice there is one arbitrary constant. This constant can be any value that you want. This is a first order differential solution. But if we were to have a third order differential equation, like dy dx plus d squared y over dx squared plus 2 d cubed y over dx cubed equal to a value of 0, we would expect that since this is a third order differential equation, the largest derivative is a value of 3, that we would have, hopefully we all recognize, 3 arbitrary constants in the general solution, So if we think here, I always like to think of this in terms of pictures. If we think there is a general solution to some differential equation, from this general solution, we can pull out all of these other solutions. So a unique solution. We could pull out another unique solution. And there are usually an infinite amount of unique solutions you can extract from the general solution, all because that constant that's in that general solution can change. It can be 2, it could be -1/2, it could be square root of 3, it doesn't matter what the constant is, but that provides a unique solution. So let's go ahead and look at that prior example. Let's go ahead and look at that prior example of dy dx minus y equals e to the 2x. And we said there is a general solution of y equals to e to the 2x, and I think it was plus ce to the 2x. And again, in this video, we don't have to determine, we're not learning how to determine the general solution of a differential equation. We're just looking at identifying a general solution and how we know it's a general solution to, and there it goes again, to that first order differential equation. So how it is a general solution to that first order differential equation. You can use an inferential property. You can recognize that there is one constant there, so this is probably the solution to a first order differential equation. Let's go ahead here and find y prime. Y prime will be 2e to the 2x, and this will be plus, taking the derivative of this second part. C is just a constant, and we're going to assume it's not equal to 0 in this circumstance. Then we're going to have 2c e to the 2x power. And let's go ahead now and plug this in to this and make sure that we get e to the 2x. So we're going to have 2e to the 2x power plus 2c e to the 2x power. Then we have to subtract our original value of y. We're subtracting original value of y because that's what the equation says to do. So we're going to have e to the 2x power plus ce to the 2x power. And this has to equal to, excuse me. I'm sorry. Let's go ahead. I made a mistake. That the exponent here is not equal to 2. It's just equal to a value of x. So I do make a mistake there. I did make a mistake. I'm sorry that, and you'll see how this doesn't. So we'll actually show a check how it's not. So let's go ahead and assume that this was a value of 2. When I go ahead and solve this, I should get e to the 2x as a final value. But notice when I distribute that negative, we're going to have 2e to the 2x plus 2ce to the 2x power. This will be minus e to the 2x minus ce to the 2x power. So now when I simplify, we realize that we're going to be left with e to the 2x power. And then we're going to have plus 2ce to the 2x minus ce to the 2x. I can pull a value of c out. So we'd have t to the 2x plus c, 2e to the 2x minus e to the 2x. And this would just give us a value of e to the 2x plus ce to the 2x. And notice that is not what we started with. So this is not, I'm sorry about that, not a general solution. So I'm sorry about that. My blackboard seems to be disappearing and causing me some confusion. So let's go ahead now and actually find, let's go ahead and apply the correct general solution. So the correct general solution to that differential equation is y equals to e to the 2x, e to the 2x plus c, e to the x power. And this is for the differential equation y prime minus y equals 2 e to the 2x exponent. So now when I find y prime, this will give me 2e to the 2x, taking the derivative of the first guy, taking the derivative of this, c is just a constant not equal to 0, so we're going to get c e to the value of x. So now when I plug into my original differential, we're going to have 2e to the 2x plus ce to the x. We're now going to subtract our original solution, our original general solution, so we're going to have e to the 2x plus ce to the x. Let's distribute that negative, so we're going to have 2e to the 2x plus ce to the x minus e to the 2x minus ce to the x power. Notice here that we have 2e to the 2x minus e to the 2x is just going to give us e to the 2x. Positive c to the x minus c to the x gives us a value of 0. And notice, that's what our solution, that's what this was equal to. So this is in fact the correct, this is the correct general solution to that first order differential equation.